name is Alberto Marquez. In this video, we will discuss how to create a simulation model of an MM1 system. To do this, we will use Excel. So we start with a clean spreadsheet and we set up the parameters for a MM1. First, the value of lambda, let's set it up to 5. And the value of mu, the service rate, we set it up to 6. So we proceed to identify the entities. Let's consider entity 1, entity 2, entity 3, and so on. Let's set up a few of them. Then we are going to define the arrival time. The first entity arrives at 0, just because we're starting the simulation. And then we need to program the next arrival at this time. We want them to follow an exponential distribution, so we need a random number. And this is a uniform random number between 0 and 1. From there, we transform this random number into an exponentially distributed interarrival time. So the next arrival time, or in other words, the time between arrivals, is the formula that we need for the inverse would be negative natural logarithm of 1 minus the random number divided by lambda. And we always use that lambda, so we make the value absolute. Once we have that, now we need to define when the entities arrive, starting service at the server. So starting service, because it's the beginning of the simulation, there is no other entity in the system. So for the first entity, the service time, the starting service time is just the same as the arrival time, just for this one. And then we need to determine the service time, the total service time for when the server is processing this entity. To do that, we need another random number. So we generate another uniform random number, and now we determine the service time. Service time, we will use exactly the same formula, or a very similar formula, which is negative natural logarithm of 1 minus the next random number, divided this time by mu. And also we need to use an absolute reference. So that's the service time. So the finishing time or ending time for this process is the starting service time 0 plus the starting service timing clock plus the service time, and that's where the entity ends its service and departs. Now we're going to the second entity, and the second entity will arrive at the previous arrival plus the time between arrivals. This is a schedule based on the random number and the event program from the previous entity. This is how a discrete event works. The events are scheduled beforehand, and we know that this second entity will arrive at that time. The numbers are changing due to the random numbers, but the formulas are the same. We need another random number to schedule the next arrival. Very good. Now the service time gets a little tricky because two things has to happen if it's an MM1. The server has to be available and the entity should have already arrived. So in order to compute that, we will use the maximum between the arrival time, guaranteeing that the entity already arrived, and the departure or finish of the previous entity, guaranteeing that the server is available. And in this particular example, just as it is, remember the numbers will change because it's the randomness of the numbers. But right now at point 31, the arrival happened after the finishing time, so the starting of the service happens only after the second entity arrived. Very likely when I put other numbers, in some instances, you will see that that entity has to wait. So now we schedule the service time by generating another random number and repeating the same formula and repeating the same finishing time. And now you can see in this particular instance that the starting service for the second entity, the starting service time, depended on the availability of the server because the next entity arrived pretty fast. So the second entity had to wait. Okay, now we can copy this down. And there you go. You have a complete simulation model of an MM1. We can make it more readable by formatting the numbers a little bit. And we can make some computations. One first computation is, do we have to wait? Was there any wait for the server to be available? We can ask that question by asking if the starting service time was equal to the arrival time, then there was no wait. Otherwise, yes, there was wait. And you can see in this particular case, most of the entities waited. But depending on what the random numbers are, now you see patterns in which sometimes they wait, sometimes they don't. Well, can we compute how much they waited? Sure we can. We can compute the difference. That will be the waiting in line, and that is going to be the difference between when we started the service minus when we arrived. For the first one is 0, but the others may have a different number. And we can estimate the total time in system by using a variation reduction technique. The average service time will be 1 over mu. We have the formula to be WQ plus 1 divided by mu, which was defined as 6. Let me copy this down. Very good. We have now 21 entities. In order to make it more representative, let's compute a few hundreds of these. Say, for instance, just a little bit over 1,000. And now we can compute the average of these columns. But let's not compute the first 100 because at the beginning we know there was 0, and that could influence the outcome, make it biased towards a lower number. So we can compute the average, say, from a few numbers down, and we can compute the waiting time in line. So now what we can do is we can generate This would be just one run, but we can generate several hundred runs and compute the average of the averages. So now what we do is we take that number of the average, and what we do is we are going to have 30 rows and 10 columns. And we're going to highlight this region. Here I have the formula for W and WQ. Let me put them aside. What we do is we select these 300 cells, and we will generate 300 instances of this simulation by doing data what if analysis, data table. This is not what originally was intended for. However, it works very nicely by selecting a couple of empty cells, and then we hit OK. And now we have 300 instances, each one with some 900 entities. So now I can compute the average of all these many instances of the average time in the system. And the average comes to be 0.8320. The results from Q in theory we would expect to be that the W is 1. The concept is WQ and W from the experiment or simulation. This is what we're getting, and by using the rule for the 1/6 as a service time, we would add 1 divided by mu and using the formula for WQ equals 1/6 minus 5, which is just 1, and then we can subtract the 1/6 from that. This minus 1 divided by mu, and you see the actual numbers in the experiment fluctuate very close to what we would expect from the theory. This is a sampling process, and therefore we would need to take several of these into consideration. If we go back to the original table that we prepared, you will notice that each one of these entities can be computed with their own waiting time in line and the waiting total time, and therefore W and WQ are entity-based statistics. Because each entity contributes with its own data to the overall result. The question on how do we compute the L, it's a little more tricky. And for that, we will see another video.